My name is Cizerle, and I'll be speaking about my ECTE451 thesis topic, which is titled Analyzing the Effects of Distributed Generation on Distribution System Reliability. My thesis supervisor was Dr. Ashish Galgaonkar. I'm pretty sure I'm not pronouncing that correctly, but that's all right. As an introduction, there is a big shift towards renewable energy as a replacement for fossil fuel technologies at the moment, with climate change becoming an ever more prominent topic in politics around the world. The push for renewable energy to replace these dwindling resources is becoming more and more prominent. And with that shift towards renewable resources, we must understand what the reliability of these technologies are, especially when added into existing distribution system architecture. So this thesis addresses the addition of distributed generation, which is small scale up to about 100 kilowatts to a megawatt size generation systems, primarily from wind and solar power, which I'll go into more later, and their effects on distribution system reliability. As I mentioned before, this thesis will address the effects of distributed generation on distribution system reliability. And one of the most important factors to consider is the time variability of solar generation and of wind generation. Obviously, the wind isn't blowing all the time, the sun is not shining all the time, and with that, there are challenges for how a system can react if there is suddenly no wind, or if there is suddenly a cloud and the power generation from these systems goes down. Can the system still survive? Can customers still receive the power that they need? And how does that affect the overall distribution system? On the other side of the coin, if an existing feeder gets knocked out and you still have this source of renewable energy, then does this improve the overall reliability of the system by having a second redundant supply which can at least supply some of the system with the power required? So the way that I've decided to address distribution system reliability, obviously I can't build my own distribution system. It's not feasible to do so. So I have simulated a distribution system with and without incorporating DG, distributed generation, and analyzed the effects of DG on the system reliability. But then the question arises, how is that done? How do you quantify the shift in reliability? Well, the change in reliability is measured using specific indices that have been defined by the Australian Energy Market Commission. These indices are based on whether customers are receiving the power they need, how many interruptions occur in a given time frame, usually a year, how long these interruptions last for, how quickly are they repaired, how much of the system still has power of the total system, and how much time does the system spend up and operational in a given time frame. These indices that have been defined are then sent to DNSPs, distribution network service providers, as a standard to which they must keep the network to. The network must maintain these standards of reliability to ensure customers are receiving the power that they need in any given time. If the standards are not met and they're not meeting the indices standards that are set out to them, then penalties will be given to the DNSPs, and if they exceed the recommendations by the AEMC, then rewards will be given back as a financial incentive. So a big target of this thesis and of future work will be to try and quantify money-wise what a positive effect on reliability by renewable sources of energy would do for this penalty versus reward system. That penalty versus reward system is called STABALISED. It's a scheme developed by the AEMC, and yeah, that's basically the idea. These graphs just illustrate the time variability of wind energy, not too important. So there are two main types of reliability in electrical distribution systems. There's equipment side reliability and there's customer side reliability. Equipment side reliability is intrinsic to the equipment itself. How long will a given piece of equipment last? How often does it need to be replaced? How long does it take to dwindle? These are the questions for equipment side reliability. That's not the focus of this thesis. This thesis will be addressing customer side reliability, which has to do with the indices set out by the AEMC, and is more focused on whether customers are getting as much energy as they need and are online for as long as they should be. So that's again mentioning that the AEMC has set out these standards which are given to DNSPs, and they must keep up these levels of reliability in an electrical system. And first time mentioning that STABALISED is the scheme set out to reward or penalize DNSPs on whether they meet these reliability targets. So the indices I mentioned before, primarily the most important ones, are SAIFI, SAIDI, CAIDI, and ACE. You don't need too much of an understanding, but SAIFI is basically concerned with how often interruptions will occur in the distribution system. SAIDI is concerned with how much time the system will be down for. CAIDI is much the same, but from a customer's perspective instead of a supplier's perspective. And ACE is concerned with the amount of time as a fraction of 1 that the system will remain up and active. So 0.99999 would be quite good, 0.5 would be atrocious. Now to do this and to simulate a system, I've decided to use Cizerle. It's a powerful tool for people to use to simulate a distribution system, and it also has an incorporated reliability assessment toolbox. This can be used to churn out the indices that I'm concerned with, and therefore relate these indices back to what money can potentially be saved by DNSPs if they incorporate renewable energy into the system. If renewable energy increases the reliability of a system, therefore it would decrease the financial penalties they have to pay or decrease the amount of infrastructure spending required on the network itself, and therefore is beneficial economically to the DNSP, which is a further incentive to keep investing in renewable energy. Now, the way that I will do this, the simulations, is to construct two networks, distribution networks. One without DG incorporated, and one with DG incorporated in the form of 2 solar PV generators and 2 wind turbine generators. And then compare the reliability assessment toolbox results of the 2 networks together and determine which network is the most reliable. From there, we can get a good baseline understanding of the effects on reliability that distributed generation has on a distribution network. The time period of each simulation was also a year, and the equipment reliability statistics used are those acknowledged by the IEEE. So it is a universal standard and should be a reliable baseline for further work later in ECTE451 or just in further research in general. This is a bunch of data that is obviously not meant to be understood right now, but these are basically some of the results that are churned out by Cizerle after running both systems through the reliability analysis toolbox. We have all of our reliability indices shown and a few more that I didn't mention. And this presents a pretty good picture if one has a good understanding of the reliability indices of how the reliability is affected when DG is incorporated. Now, the main findings that I found by completing these simulations were that the safety of the overall system was a lot less for the system with DG incorporated. This is because even when a feeder is disconnected from an existing power supply, the distributed generation in a radial system is still able to supply some customers with power, even though there is no normal way to supply customers. With a bit of fancy switching and circuit breakers in the distribution system, it is possible to supply some customers with power and therefore decrease the overall frequency of interruptions in the network. Now, the KFI and KD will stay the same. This makes sense, as whenever a fault occurs in the network, it will take a few hours to repair. No incorporation of distributed generation will change that. It's just going to take a set time to repair a fault, and so that's expected. Obviously, for the same reason, the AC will increase for the system with distributed generation, as in the network will spend more time operational if you incorporate distributed generation to the system, as some customers will still be able to receive power if a normal feeder is disconnected. So basically, in summary, the DG does have a favorable impact on the overall reliability of the system. As an additional point, the expected interruption costs, or EIC, another indice laid out by the AEMC, has decreased by half in the system incorporating DG. If a industrial system loses power for a long period of time, it obviously would cost the DNSP some money because they're meant to upkeep the system for as long as possible. But with the addition of a distributed generation in the form of renewable energy, then perhaps that industrial plant could remain running during that time, and therefore they wouldn't have to pay interruption costs to any customers or anything for that. Now, the conclusions gleaned are that the overall reliability of the system was improved, and with a fairly low penetration of renewable energy into this system, the effects on the system were favorable. As the penetration level of renewable energy increases, and therefore the time variability of the system increases, it would be interesting to see how this could potentially negatively impact the reliability of the system, as existing technologies are slow to react to large power changes, which can happen when you're using wind turbine generators. If the wind suddenly drops off, how does the system compensate for that? Put more coal in a power station? It's a tough question. So the most important result possibly gleaned by this is that there is a chance that introducing renewable energy to a system can positively impact this stiffest plan that I described earlier, and can potentially save DNSPs money by reducing the amount of money that needs to be spent on electrical infrastructure to maintain the same levels of electrical reliability. That's a very important point, and is probably the most promising aspect for further research. If this could be nailed down in further research to an actual dollar value, and distribution systems could be more closely simulated to existing distribution systems, we could see a real-world application and incentive for further renewable energy spending. So as I mentioned in the previous slide, increasing the size of the distribution systems modeled into more real-world applications is a pretty good way to further research this area of study and to try and get a real dollar value back to this stiffest plan, and to try and glean what the positive effects financially could be if we incorporate DG into our distribution systems. Alright, thanks for watching.